Alright, so today we're going to look at properties of salts. And we're going to determine whether or not salts are acids or bases, and also determine their pH values. So first, a reminder that salt is just another name for an ionic compound. And of course, when we dissolve ionic compounds in water, they break up into ions. So if we look at this problem here, where we're looking at salt as a weak base, if we put sodium acetate into water, right, what are the major species that we have present? Well, we would have sodium ions, and then we would have acetate ions. So then what happens to those when you put them in water? Well, the sodium could combine with the hydroxide ions, right, in the water, but that would form sodium hydroxide. And we know that sodium hydroxide is a strong base, so it completely ionizes, so those two things would not actually come together. And then the other species that's present in water is hydrogen ions, and when it would come into contact with the acetate ion, it would form acetic acid, which is a weak acid. It's not one of our strong acids, so it's a weak acid, and therefore would stay together since it does not completely dissociate. And so what happens is we have our acetate ion in our water. The water gives the acetate a hydrogen, and we get acetic acid. And then we're going to be left over hydroxide ions. And since we have this leftover hydroxide ion, this makes our base or salt here basic. So then we can determine our pH value for this. But first, we need to do that. We need to determine what the Kb is. Since we form hydroxide, we need a Kb value. And so we look up our Ka on our Ka chart for acetic acid, and we find it's 1.8 times 10 to the minus 5. And so then to calculate our Kb, as we learned in a previous video, we have 1 times 10 to the minus 14, or Kw, divided by our Ka, and that gives us 5.6 times 10 to the minus 10 for our Kb. Then we want to set up our equilibrium expression. So it'll be our Kb is equal to our acid concentration times our hydroxide concentration divided by our acetate ion. Right, so now we want to calculate our hydroxide concentration. So in order to do that, we want to set up our ice chart. So we'll rewrite our equation here so we can make our ice chart. Okay. And so what is our concentration of our ion to begin with? Well, it was 1 molar, so it told us the salt was. And so since it's 1 to 1 with the salt, it's 1 molar here as well. And then our change line will be minus x plus as we dissociate some. And so equilibrium we have 1 minus x, and x. So then we can plug all the information in to our equilibrium expression. So we have 5.6 times 10 to the minus 10 equals x squared over 1 minus x. We use our solver to find x, and we discover that it's 2.4 times 10 to the minus 5. So remember that x corresponds to our hydroxide concentration, right? And so from there we can find our pOH by doing the negative log of 2.4 times 10 to the minus 5. And then our pH would be 14 minus that. And so when we do that in our calculator, we get 4.62. So then 14 minus 4.62, and we get 9.38. And to know that our answer makes sense, that is basic, and since we're forming hydroxide in our reaction, we should have a basic pH. Alright, so go ahead and pause and try to do the practice problem on your own, and then come back and we'll go through it together. Alright, so first we want to determine what is the reaction that's actually going to happen here. Sometimes you get a hint when they give you the Ka value. They tell you what's actually happening. But as a review, remember sodium ion would combine with hydroxide from sodium hydroxide, which is a strong base and doesn't actually form since it completely dissociates, which means that our fluoride ion is the one that's going to react with our water to form HF and hydroxide. Again, that's because the water gives the fluoride ion hydrogen. So we set up an ice chart. Our initial concentration was 0.3 and none on this side. And then we shift to the right, and at equilibrium we'll have 0.3 minus x, x, and x. We do need a Kb value since we have hydroxide, so we use the Ka they gave us to find our Kb. So we'll do 1 times 10 to the minus 14 divided by our Ka, 7.2 times 10 to the minus 4, and we get a Kb value equal to 1.4 times 10 to the minus 4. We write our equilibrium expression, our Kb equals concentration of HF times OH over the concentration of our fluoride ion. And we plug in what we know. Our Kb of 1.4 times 10 to the minus 4 equals x times x, which gives us x squared over 0.3 minus x. We use our solver, solve for x, and we get 2.0 times 10 to the minus 6, which is, x is going to be representative of our hydroxide ion concentration. Right. And so then we can find our POH by doing the negative log of the hydroxide concentration. And we get a POH, which is equal to 5.70. And then you get the pH. We subtract that from 14. And we get 8.30. Again, it should be basic since we're forming hydroxide, and indeed it is basic. So let's look at examples where it's acidic. So for an acidic salt, in this case we have NH4 and the chloride ion. So again, your NH4 plus and your chloride ions in solution. Again, if we put that in water, what happens? Well, our chloride ions would come in contact with our hydrogen ions. That would form hydrochloric acid, which is one of our 6 strong acids. And so it would completely dissociate, so those two things would never actually come together. And so the reaction that is actually happening is our NH4 in water. And the NH4 is going to give a hydrogen to the water and form NH3. And in this case, the hydronium ion, which is the same thing as the hydrogen ion. If we set up our equilibrium expression, that's Ka is equal to the NH3 times the hydronium ion, and that's going to be divided by the NH4, the ammonium concentration. We need to determine our Ka because they gave us a Kb. So to determine the Ka, we would take 1 times 10 to the minus 14, divided by the Kb they gave us as 1.8 times 10 to the minus 5, and we get 5.6 times 10 to the minus 10. So then to solve for our concentration of hydrogen, we use our reaction here instead of our ice chart. Right? So we have our ammonium and our water forming our NH3 and our hydronium. Set up our ice chart. Sorry. And our initial concentration was 0.1 molar, and we have none of each of those. We shift to the right. So at equilibrium, we have 0.1 minus x, x, and x. We plug into our equilibrium expression. So we have our 5.6 times 10 to the minus 10 equals to x squared over 0.1 minus x. Use our solver to solve for x, and we should finally get 7.5 times 10 to the minus 6, which in this case is also our hydrogen ion concentration. Right? And so for our pH would be the negative log of our 7.5 times 10 to the minus 6, which gives us a 5.12, which is indeed a acidic pH. Right, so pause and you do the next problem. Oh, there's not a next problem, sorry. We'll do more problems tomorrow in class. So it basically works the same as the base did. Alright, so we're going to look at the relationship between K and pH for salt. So we can determine if it's acidic or basic just based on the Ka value. So the one that is stronger, the one that's a stronger acid would mean that you have an acidic pH, and if you have a stronger base, you have a basic, and if they're of equal strength, then you would have a neutral. So if your Ka is bigger, then it's going to be acidic. If your Kb is bigger, it's going to be basic. And again, if they're equal, it'll be neutral. So here we have ammonium and acetate. So we have our ammonium ion and our acetate ion. Right? So the ammonium would be our acid, and our base would be the acetate ion, since it doesn't have hydrogen to give. Right? So we would look at the Ka for the ammonium ion, which is 5.6 times 10 to the minus 10. And we have to find the Kb for the acetate ion. If we look up the Ka value for acetic acid, we find it's 1.8 times 10 to the minus 5. And so we have a 1 times 10 to the minus 14 for our Kw, divided by 1.8 times 10 to the minus 5, gives us a 5.6 times 10 to the minus 10. So in this instance, our Ka equals our Kb, and so that makes this neutral. Alright, so we do the same thing for the next one. We look up our ammonium ion, which would be our acid, and then our base would be the cyanide ion. So again, our Ka, 5.6 times 10 to the minus 10. We would need to calculate our Kb for the cyanide. So we look up the Ka value for the cyanide ion, and we find that it's 4.9 times 10 to the minus 10. We calculate the Kb by dividing the Kw by the Ka, and we get 2.0 times 10 to the minus 5. So then we want to compare those, and since your Kb is bigger than your Ka in this instance, this would be a basic salt. The next thing we have is aluminum sulfate. So we end up with aluminum ions and sulfate ions. So this one's a little tricky, right? So aluminum forms this weird complex with water, and it gives you 6 waters attached to the aluminum, which that part doesn't really make that much difference. But what really matters in this case is your sulfate, right? And so if you think about your Ka for your sulfate, it says it's very large, and that's because it's a strong acid. So if we were to think about what would be the Kb for that, we would have 1 times 10 to the minus 14 divided by a very large number, which means this ends up being a very small number. So regardless of what the Ka is for this, right, and you'd be given that, okay, not in this case, but you would be, and then this, it would be a very small number, because you're going to divide this 10 to the minus 14 divided by a very big number, and so your Ka is going to be extremely small. I mean, your Kb is going to be extremely small, and so that would mean that your Ka, is going to be much bigger in this instance, and that would mean that this would be an acidic. So if you have a situation where you're not sure what the Ka is or what happens, look at the other ion, and it can help you to figure that out. Alright, so we're going to be working on more problems like this tomorrow.